Okay, hi everyone. So, welcome to this lecture on link prediction. So we have started discussing about how we can predict links using different heuristic-based approaches, and so far we have discussed simple metrics that people used for link predictions, and some of them are very useful. For example, we have seen in the last lecture there is something called atomic adder distance, right? So atomic adder distance, although it's very simple, but it turned out to be a very competing baselines for for many settings. So today we will discuss two models, okay, and both of them are both of them are quite sophisticated in the sense like you will see one of the models which is called probabilistic model. This model will basically convert a network to a tree-like structure, and from tree-like structure we will calculate some probabilities and we will use those probabilities to calculate the similarity between nodes, okay, and based on the similarities we will then rank the pairs depending upon their likelihood to be connected. And the second model that we will discuss today is something called supervised random walk. It's one of the breakthrough in the area of link prediction, and we will see that how link prediction can be treated as a supervised learning problem, and how we can incorporate node attributes, edge attributes into the learning process. Okay. So far, if you have seen the matrix carefully, we have not considered any network, any node-centric features or edge-centric features. We have just looked at the topologies, and based on the topological structure, we basically calculated the similarity. In the probabilistic model also, we will see that we will look at the topological structure and we will calculate the similarity between a pair of nodes. But supervised random walk, which we will discuss today, is the first method where the attributes can also be incorporated, right? So along with the topological structure, you also incorporate the attributes for link prediction. Okay, so let's get started. So let's start with the probabilistic model. Okay, and basically, what is the idea? The idea is that every network. So the idea is that when nodes are linked, right, nodes are connected through links, they essentially form some sort of hierarchy, and the hierarchical structure is something which is inherent to the network, right? It may not be explicitly visible in the network structure, but it is inherent, and due to this inherent structure, the nodes are connected. Inherent hierarchical structure, the nodes are connected. For example, say if you think of an institute, right, and nodes are different individuals in an institute, can be students, can be teachers, academic staffs, and so on and so forth, right? Two students belonging to the same class, they interact quite often, and therefore they are connected. Okay, then on top of that, if you think of a discipline, right, say science, engineering, arts, right, oftentimes we see that, okay, some people from science, some people from arts, they go to the they go to gym, for example, every day, and therefore they interact with each other quite often, and therefore they are connected, right? So this you see some sort of hierarchy, right? The hierarchy basically says that you have a department. You are connected due to you belonging to the same, both of you belonging to the same department. You are connected because you go to the gym every day, right? You are connected because of some other common reason, and so on and so forth. Then again, this this information can be clubbed together to form another level of hierarchy, and so on and so forth, right? So basically, in the probabilistic approach, what it does is that it tries to unfold the underlying hierarchical structure from a network. So what we will do here, we will construct a dendrogram, right? What is dendrogram? Dendrogram is basically a tree. Okay, so we construct a tree because tree is essentially a representation of a hierarchical structure. We convert a network to a dendrogram or a tree, and then we try to understand, the probability that two nodes are connected due to certain similarities. Okay. So what is the goal here? As you see here, if this is the network, right, where this solid lines are basically those which these solid lines indicate links which have already been formed. Okay, and the broken lines are basically links which may form in near future, which we'll try to predict. Okay, so what we do is that from this network we create a tree like this. In fact, one can argue that multiple such dendrograms can be created from a network. Okay, then if multiple dendrograms can be created, now how do we create a dendrogram? We'll discuss. Okay, if multiple such dendrograms are created, then which one to choose, right? So what we do after that, once you convert a network to a dendrogram, then we calculate the likelihood of a dendrogram. For example, say A and B are connected, right? I can say that okay, A and B are connected because say they belong to the same class, right? Somebody can say that okay, no, they are connected because they go to the same they go to the gym together. Okay, so there are different notions of connectivity, and based on that one can create different types of dendrogram. For example, you see that what is the, now let's look at one dendrogram. Okay, let's look at this dendrogram 1, D1. So you see that in the dendrogram, all the leaf nodes, so this is a tree, all the leaf nodes are basically nodes in the original graph. There are 6 nodes, A, B, C, D, E, F. You see A, B, C, D, E, F, right? Now, now with 6 nodes, there are exponential number of possibilities of creating dendrograms, right? You connect A and B, right? So in this particular dendrogram, A and B are first connected, then A, B are grouped, and then it is connected to C, then it is grouped and connected to D. At the same time, E and F are connected, then E and F again are the group is connected to the group that is constructed here, and then finally this is a tree. One can say that okay, I will first connect A and B, right? There is no principled way of creating the dendrogram, right? What I'm saying is that given a set of nodes, one can have exponential number of such dendrograms possible, right? Because you have n number of leaf nodes, so n minus 1 number of internal nodes are there because it's a tree, right? You see here 1, 2, 3, 4, 5, so 5 internal nodes. You can create these 5 internal nodes in different ways, right? For example, you can connect A and C first, and then B and D first, and so on and so forth, right? Let us assume that you have some ways to create a dendrogram. Okay, and let us start with considering only one dendrogram at a time. Okay, later I will tell you how to how to convert, I mean how to consider multiple dendrograms for creating the links at the end. Let us consider that you have this graph, okay, and you have a dendrogram D1, and this dendrogram essentially tries to capture the relation between nodes in some ways. And let's look at the internal nodes, the meaning of the internal nodes. What does it say? For example, this R0 is an internal node. Remember, this R0 is not a node. It is not an original node in the graph, right? R0 is just an internal node in the dendrogram, a representative connection in the dendrogram, right? So for every such internal node, you see a probability, right? 1, 1, 1 by 3, 1 by 4, 1, right? Now, what is this probability? Now, for every internal node R, there is an associated probability PR. Now this PR indicates how likely two nodes or groups are to form a connection given R as their least common ancestor. Let us try to understand statement, right? What it is saying, that say this is R, okay, and the probability is 1. So it basically says that what is the, and let's look at the left child and right child. Left child is A, right child is B. So this probability 1 indicates the probability that node A and B are connected. Similarly, say let's look at R2. Okay, the probability is 1. It indicates what is the probability that this group, so look at left child and right child, right? So left part we have AB and right part we have C. What is the probability that one node from left child, left part, and another node from right part are connected, get connected and form an edge, and the probability is 1, right? So you see the point here, right? So let me read this line again. Each internal node R has an associated probability PR, which indicates how likely two nodes, in this case 2 nodes, but if you consider R2, then this is one group and this is another group, right? How likely 2 nodes or 2 groups are to form a connection given R as their least common ancestor. Look at R, look at R0. So R0 is the least common ancestor of A and B, right? R2 is the least common ancestor of A and C or B and C, right? Because A and B can have other ancestors. For example, R2 is also ancestor, R3 is also ancestor, right? But R0 is the least common ancestor. Okay. So now how do we calculate this probability? We will discuss. So let's try to understand this tree again, right? In this tree, let us assume that we have some ways to create a dendrogram. We have a dendrogram, right, where leaf nodes are original nodes in the graph, right? And internal nodes indicate some sort of association between nodes, right? And each internal node is associated with a probability, which basically indicates the likelihood that two nodes are to form a connection, right? Given that R, the internal node R, is the least common ancestor. Okay. So now let's focus on the dendrogram again. So what we have not discussed so far, we have not discussed how to create a dendrogram. So we assume that we have, I mean, we are given a dendrogram, right? We have also not discussed how to measure these probabilities, right? Let us assume that we also know the probabilities associated with the internal nodes. Okay. Now think about it. So let's assume that this is an internal node R, and you have a node here, you have a node here, and you have PR. Right. Right. So let's assume that the left part has 2 children and the right part also has 2 children. Okay. So this is AB, this is CD. So how many possible edges can be there? Can be formed. An edge can be formed with AC, because I mean the way you create the dendrogram is that you can't take 2 nodes from this 2 nodes from the same side. It is not possible that you take A and B, right? What you need to do, you need to take 1 node from left part, 1 node to right part, and then you see whether these 2 nodes are connected at all or not, right? So how many possibilities are there? How many possible edges can be formed? One is AC, other is AD, then BC, and then BD, right? So AC, AD, BC, BD. Okay, and out of these 4 possibilities, how many possibilities have already been materialized in the graph? Meaning that out of all these 4 pairs, how many pairs have formed edges in the network, right? So for that we need to go back to the network, right? For example, if you think of say if you think of say is R3. Okay, so you have this group and you have this group. So what are the pairs? The pairs are AD, BD, and CD, right? And now let's look at the original graph. So AD is not connected, so this pair has not been materialized. BD is also not connected, right? Because this broken line is basically indicating that whether it will be connected or not in the future. So these edges are not there. So BD is also not connected, but CD is connected. Okay, so what we do here, for every such internal node R, we will see that how many number of edges in G is the original graph. How many number of edges in G whose endpoints has R, whose endpoints have R as the lowest common ancestor in D, right? For example, in this case, you have pairs AC, AD, BC, BD, and we will see, let's assume that A and C are actually connected in the graph, original graph. A and D are also connected in the graph. This is not connected, this is not connected. Okay, so ER would be 2. Okay, what is LR and RR? LR is the number of left side leaf nodes and RR is the number of right side leaf nodes. Very simple. In this case, LR is 2, RR is also 2, right? So LR times RR will essentially tell you the possibilities number of pairs, in this case 4, right? So out of LR times RR number of pairs, ER number of pairs have actually been materialized as edges in the graph. Okay, all right. We also know the probability PR of being connected. Probability PR, that 2 nodes, right? 2 nodes which are connected to 2 nodes which are descendant of the internal node R are connected, right? So now what does it mean? So now what we do is that the probability of probability that each of the original edges, so there are 1, 2, 3, 4 possibilities, right? And among them ER number of edges have are actually there, right? So and we are assuming that these edges are formed independently. So what is the probability that these edges exist due to the internal edge, the internal node R? The probability would be PR to the power ER. PR is the success rate. PR is the probability that nodes are connected, right? And how many such nodes are connected? ER number of nodes are connected. So PR times PR times PR dot dot dot. It will go on for ER times. Nodes are independent. Edges are independent of each other, right? So what is the probability of success? So think about it. ER number of nodes, ER number of pairs are actually connected. And how many number of pairs are not connected then? LR, RR minus ER, because these are the total possibilities, and this is the number of edges which are already there, right? So the failure is basically 1 minus P, right? 1 minus P is the probability that nodes are not connected, right? And how many such cases are there? LR, RR minus ER. So for each internal node, the probability of success is PR to the power ER times 1 minus PR to the power ER LR RR minus ER. Now this is for a particular node R, right? So for all the nodes, for all the internal nodes in the dendrogram, right? So now what is the target? The target is to measure the likelihood of the entire dendrogram, right? We know the probability of each internal node. What we do, we basically take the product of all the internal nodes, and that will give you the likelihood of the dendrogram. Okay, this is simple, right? Now this is the likelihood. What is unknown here? Unknown is PR. We do not know PR. And remember here, PR is dependent on R, right? PR is not uniform across all the R's because this is dependent on the internal nodes. So what we have done so far, from a given graph G, V, E, right? We have created a dendrogram D, V, PR, right? D, V, PR, right? Whatever, V or mod V, whatever, doesn't matter. Now remember, this PR is not a single number. PR is basically a vector. For every R, we have a probability, right? Now this notation is similar to what we have discussed something earlier, long time back. Think about it. This notation is same as what? Ardos Rennie's random graph model. You remember the random graph model that we discussed? G, N, P. The random graph model in the network in the graph model chapter, right? What was the discussion? So basically there the idea was that how do we create a random network, right? So we have n number of nodes, we choose a pair of nodes randomly, and then you toss a coin. With probability P we connect, with the probability 1 minus P we do not connect. This is also kind of same, but not exactly, because here the major difference is that in that random graph model, the probability of forming an edge was uniform. Everything was P. But in this case, it is PR, and PR is dependent on the internal node, right? And the random graph model doesn't actually explore the hierarchical structure. So it basically explores a kind of hierarchical structure. But the common part is that both the dendrogram and the random graph model assume that edges are formed independently, right? Meaning that the formation of an edge is nothing to do with the formation of the other edge. They are independent. Therefore, we write this kind of formulation. Okay. All right. So now this is the likelihood of a dendrogram. Similarly, if you are given another dendrogram, you can easily calculate the likelihood of a dendrogram, assuming that you know the PR. If you know the PR, you can measure the likelihood of that dendrogram, right? Now, what is our target? Our target is to come up with a dendrogram whose likelihood is maximum. Our target is to come up with a dendrogram whose likelihood is maximum. So we try to maximize this likelihood, right? So maximize likelihood is same as maximize log likelihood. All right. So what we do here is that, let me so what we do here is that let me write it again. L of D PR is basically product of all R belonging to the dendrogram D, right? PR to the power ER 1 minus PR to the power LR minus ER, right? So we want to maximize this, okay? And when we maximize the likelihood, we generally take the log likelihood, right? We take the log. So we take the log in both the sides. So if we take log here and log here, it will be log of, right, product will be basically sum over all R belonging to D, log of PR to the power ER, right, plus log of 1 minus PR to the power LR minus ER, right? Okay, and this is summation of ER log of PR plus LR minus ER log of 1 minus PR, right? Okay, now we need to maximize this, and unknown is PR. So what we do, we take the differentiation, right? So del L del PR is essentially summation of ER, right? 1 by PR plus LR minus ER minus 1 by 1 minus PR, right? So this is ER. Okay. So PR times 1 minus PR. So ER into 1 minus PR minus LR minus ER into PR. Okay, simply I'm just taking the derivative, right? And something that we want to maximize or minimize, we take this as 0, right? And if you calculate, we see that PR, the optimal PR star, the optimal value of PR is essentially ER by LR. Okay, let's try to understand what is this. PR is the probability associated with the internal edge R, internal node R. Okay, it is very intuitive, right? You can also intuitively explain this. Out of this many pairs, this many edges exist. Out of LR times RR number of pairs of nodes responsible, which are connected to, which are associated with internal edge, internal node R, ER number of pairs are actually connected in the graph. So this is the optimal value of PR. Okay, so what we do now, since we understood that PR is essentially ER by LR minus LR times RR, what we do is that, so PR star is ER by LR minus RR. Therefore, ER is PR star LR, right? So I replace ER here by this one. Okay, so my log likelihood is essentially ER. Okay, because it's a power, so therefore it will come down. So this is LR RR PR star log of PR star plus LR RR minus LR RR PR star log of 1 minus PR star. Okay. So now if we take LR RR common, we have PR star log of PR star plus 1 minus PR star, right? Because we take LR and LR common, so the remaining part is 1 minus PR star log of 1 minus PR star. Okay, so this is one part and this is multiplied by this one. Now what is this?
Binary cross entropy.
This is entropy, right? So h of p is basically minus p log p 1 minus p log of 1 minus p, right? But the minus symbol is missing, therefore I can write it as minus LR RR H P R star, right? So this is something that we want to maximize. So there's a minus, right? So if we want to maximize, these values should be minimum. So when the entropy will be minimum, entropy, we all know the curve, right? When the entropy will be minimum, either this point or this point. So this is PR and this is H of PR, right? Star, whatever, star. So if PR equals to 0, then it is minimum. If PR equals to 1, this is also minimum. These are the 2 points. So it basically says that the highest likelihood dendrograms partition vertices into groups where the connections are either very common or very rare. So you should so R should partition, think of one node R, right? One internal node. So R should carry nodes in such a way that either they are their connections or their attractiveness between them would be very high. In that case, PR star should be 1, or it should be very less, which is 0. Okay, so now again, stop and go back. Let's think about what we have discussed so far. So what we have discussed, that from a graph we created a dendrogram. Okay, how do we create? We randomly created a dendrogram. Okay, from now in a dendrogram, we know how to measure PR, because PR is essentially ER by LR times RR, and ER can be LR, RR can easily be measured based on the dendrogram and the original graph. Right? Once the dendrogram is given, you can easily measure PR for every R. Right? So now we basically know the PR value. So from PR we can easily measure the likelihood of the entire dendrogram. Given a dendrogram, you can measure the likelihood of dendrogram. You are given another dendrogram, you can measure the likelihood of the dendrogram. Right? And what you do basically, you basically choose that dendrogram whose likelihood is the highest. Right? But the problem here is that, as I mentioned, you have a lot of such possible dendrograms that you can create. Right? So what's the strategy to create a dendrogram? What we do in that case, what the author suggested, is that you start with a random dendrogram. Okay, you can easily create a random dendrogram. Now you fix a particular R, you fix an internal node. So if you fix an internal node, what are the other components related to that internal node? The other components are, the internal node has a left subgraph, it has a right subgraph, and it also has subgraphs of its siblings. Right? So what I'm trying to say is that, let's think of this internal node. Okay, so it has this subgraph, it has this subgraph, and this is the sibling, and you basically consider the entire subgraph from a particular sibling as basically another part. Right? So you are given a dendrogram, you basically create a random dendrogram, you fix an R, right? And for every R there are 3 components: the left part, right part and the sibling part, right? And you basically randomly shuffle nodes in the left part, right part, and sibling part. If you randomly shuffle, keeping R as fixed, right, you will get another dendrogram. Okay, you get another dendrogram. Now you look at the likelihood of the first dendrogram and the second dendrogram, right? And you choose the one whose likelihood is the better. So assume that the second dendrogram's likelihood is better. So you keep this one. Again, in the second dendrogram, you fix an R. You basically shuffle the left part, right part, whatever the other components. You create another dendrogram, and then you check the likelihood between these and this. Right? This is one strategy. This is something called Monte Carlo type strategy. Okay, and in fact, the authors said that it is not necessary to come up with a single dendrogram. It is not necessary to come up with the optimal dendrogram, for this calculation. What we can do, you can actually come up with multiple such optimal, suboptimal dendrograms. Right? What it basically trying to say is that from a particular random, so you start with the random dendrogram, right? And you do all these modifications here, and you finally end up with the optimal dendrogram starting from this random dendrogram. So you keep this optimal dendrogram. Again, in the second iteration, you create another such random dendrogram, and you do all these things, and you get another optimal dendrogram, right? And let's take such 10, 15 optimal meaning suboptimal dendrograms. You take suboptimal such dendrograms, right? And you know the PR values of internal nodes of all these dendrograms. Now, how do you predict the link? That is not discussed so far. Okay, so now if we want to predict the link, right, what you do is that let's assume that these are the two suboptimal dendrograms that you opted. Okay, now you want to understand the similarity between node A and node D, or say B and D, right? So you B and D, whether B and D are connected or not. What you do, you look at the least common ancestor of B and D. What's the least common ancestor of B and D here? R3, and the probability is 1/3. Here, least common ancestor of B and D is essentially R4. Probability is 1/9. So the mean probability is 1/3 plus 1/9/2, which is the similarity. The similarity between two nodes B and D is 1/3 plus 1/9/2. So you have all sorts of suboptimal dendrograms. You look at the probability of the least common ancestor of a given pair of nodes, right? You take the corresponding probability, you sum them, take the mean. Similarly, for another pair, say BF, you can create this one. You can measure this one, right? And then you arrange the pairs based on the probability, and you basically return top 5%, top 2%, top 10% such pairs whose values are maximum, highest, right? So in this way, you can essentially predict the links. Okay, I hope you understand this part. All right, so now we will discuss another algorithm which is quite remarkable in the sense that this is the first, I guess this is the first supervised algorithm where the topological structure and the meta information are captured in a very systematic manner. Of course, you can, link prediction itself is a supervised learning problem, because essentially it's a binary classification problem. You take pairs, all possible pairs. Some of the pairs are edges, some of the pairs are not edges, right? And then you basically get a balanced data set. You train your model and test it. But so far, the method that we have discussed, they are all unsupervised. Okay, but this is kind of a supervised method, right? So what is the idea here? So the method is called supervised random walk. Okay, we know what is random walk, right? We start from a node, we basically choose an associated edge, we move through the edge, and then you basically land up to another node. From that node you choose another edge, and you basically keep on moving and moving until unless you have some destination. Okay, it's a drunk man. Okay, random walker. So so here the idea is that you start from a node, right, and the random walk happens in a biased manner. What does it mean? It means that the random walker the random walker is likely to move to through a path or through an edge whose strength is high. Forget about all this complication. Okay, let's think of a network. Okay, and you assume that is nodes and edges have some features. For example, in case of Twitter network or Facebook network, nodes can have demographic features, age, gender, occupation, right, topic, etc. Whereas edges can also have features like in case of say Facebook friendship network, say number of messages exchanged between two users. In case of following, for example, you know how many times a particular follower has retweeted a followee's tweet, and so on and so forth. These are some of the meta information about the age. Okay, so what we do here, let's look at the steps, right? What we do here is that we take into account the node features and edge features, right? So basically a vector, right? We convert a vector to a scalar. For a pair of nodes, may be connected, may not be connected, right? We know the node features, we know the edge features. So what we do, we convert this vectors, node feature vector, edge feature vector, to a scalar. And this scalar will basically tell you the strength of these pairs, right? If it is an edge, then edge strength. If it is not an edge, then a pair strength, right? So for every pair, you have a strength now, strength score, right? Then what you do, then you choose a node, right? And then you start a random walk with restart process from that node. Okay, we know what is random walk with restart. In random walk with restart, we basically, you know, do random walk with certain probability, and with 1 minus that probability, you basically jump to the original node, right? So from each node, you basically do random walk with restart. But how do you do that here? Here the random walker is biased towards the edge strength, meaning that say this is the node and these are the edges. The random walker is likely to follow that edge whose strength is high. Again, probabilistically, not deterministically. Okay. Say for example, this is a node and the strength of this one is 0.7, this one is 0.2, and this one is 0.1. So with probability 0.7, it will basically pick this edge. With probability 0.2, it will pick this edge, right? For the random walk process. So if this is the choice, then it basically follows this one. It basically moves to the next node. Again, it has two probabilities. In one probability, with probability p, it further moves. With probability 1 minus p, it moves back to the original node, right? So for every node, right, you basically get a page rank kind of score of the other nodes present in the graph because of the random walk process. It's a random walk is restart. You start from a node, right, and you essentially measure the probability, the page rank score or some sort of random walk score, right? But here, what is the learning factor? The learning factor is that I will you know, so this is basically a parameterized algorithm, parametric algorithm, right, where the parameters are being learned, and the parameters will essentially ensure you that those pairs which are connected, direct connection through an edge, right, the strength would be high. So from node feature, from edge feature, we basically measure the strength, right? How do we measure the strength? We basically use some function. This function is parameterized by W. The W is something that we learn, and the W parameters ensure that those nodes which are actually connected in the graph will have high strength, and nodes which are not connected in the graph will have low strength. Okay, so for every node we have now two samples. One is called positive sample of nodes, other is called negative sample of nodes. Positive sample of nodes essentially are those nodes which are directly connected to this node, and negative samples are those nodes which are not connected to this node. Okay, and the idea is that the random walker should basically visit the positive nodes higher than the negative nodes. This is the idea. Okay, so I have told you a lot of things. Now let's try to understand things one by one. Right? So you are given a graph. It can be a directed, undirected, doesn't matter. Right? Now for every node, say for every node, say whatever x, right? You have two pairs, D and L. What is D? D is the set of positive nodes, and L is a set of negative nodes. So positive nodes are those nodes which are directly connected to x, and negative nodes are those nodes which are not connected to x. Right? Okay. And what is this one? This is basically the attribute of the edge xy, or attribute of the pair of nodes xy. Okay, so say node x, say you have node x, node y, you have some vectors of x, a vector of y, right? You also, these are node features. You also have edge features, right? So all these things are combined, okay, using this function. We'll discuss what are these functions. Then this will now be passed through a function fw. Now this is the training function fw. So what this fw does, fw takes into account the output of this one and converts it to a value, a scalar value a. Okay. Now as you see, this function f is parameterized by w. So this w is something that we learn. Okay, this function converts a vector right to a scalar. Okay, now for every pair uv, irrespective of whether they are connected or not, right? So you can think of a new adjacency matrix, right? A modified adjacency matrix where each entry is a uv, right? A x y, a x z, and so on. Okay, this is not a stochastic matrix. This is not a stochastic transition matrix, because stochastic transition matrix makes sure that the row should be 1, the sum of values in row should be 1, and the right, if it is bistochastic, then the column should also be 1. So how do we make it stochastic? Because ultimately we use this metric for as a transition matrix for random walk process. So this is not adjacency matrix, by the way. This is a modified version of the adjacency matrix where each entry indicates the strength, edge strength, and the edge strength is computed using f. Right? So now in order to make this thing stochastic, you basically take the sum, right, divided each element by the sum, then you get a stochastic matrix. Now this matrix is used for random walk process. Okay, so as I mentioned, this is random walk with restart, right? Therefore you see there are two components with probability 1 minus alpha. You basically follow the stochastic matrix and you move with probability alpha, you jump, right? So if you start from 1, if you start from u with probability this, you move with probability 1 minus this, you basically jump to the original node. So if you do these things for every node, right, for every node u, for example, you essentially get the page rank score, the kind of a page rank score of all the nodes present in the graph with respect to that node, right? So finally, the page rank score of that node u is essentially the page rank score of all the neighbors of that node times the the entry of the modified adjacency matrix. Okay, so what we have discussed so far. We assume that we have some learning function fw, right? Parameters by w. We don't know the values of w. This is something that we learn, right? Assume that we know the values of w. From the function fw, we basically get a strength matrix. From strength matrix, we get a stochastic transition matrix. From stochastic transition matrix, we then use basically a random walk with restart kind of formulation. We get the scores of all the nodes with respect to a particular starting node. Then for the starting node, we basically take the probabilities of all the nodes and the corresponding strength, and you basically sum it up. That will give you the probability of that particular node, right? So what is the learning? Now here comes the learning part, right? So this function fw, the parameter is w. Okay, what I mentioned earlier is that I try to bias the random walk process in such a way that it would prefer the positive nodes higher than the negative node. It would prefer the positive node higher than the negative node, right? So in this page rank, right, using this page rank value, so for each node, for px, for py, for pa, for each node we get this value, right? Now for a particular node u, right, for a particular node u, now think about it. For a particular node u has a set of positive nodes d and the set of negative nodes l. Positive nodes are those which are connected, directly connected, and negative nodes are which are not directly connected, which are not connected with you directly, right? So and each of these nodes have some page rank value. I call this as PD, right? And this is PL, right? So our target would be to drive the random walk process in such a way that the page rank of the positive node PD is greater than the page rank of the negative node for all the node, for all the positive node, for all the negative node. Our target is to bias the random walk in such a way that the page rank value of the positive nodes, right, is higher than the page rank of the negative nodes. You take any pair of positive node or negative node, this should satisfy. So what is our optimization function now? Our optimization function is minimize w, meaning minimize w square, right, mod w square, such that PD always greater than PL for all D belonging to D, for all L belonging to L. Right? Why I am minimizing? I am minimizing the weights, right? These weights that we want to learn. Why I am minimizing? Why I am not maximizing? If we maximize it, then it will overflow, right? What is W? Remember, W is the parameter of the function f. So I try to minimize such that this satisfies. Right? Now, this is a very hard constraint. For every pair of positive negative nodes, I can't ensure that every time this will happen. Therefore, what I do is that I add, so this is our function, this is optimization function, and these are constants. What I do, I add a component in the optimization function itself, which is basically a regularizer. Okay, what does it say? That, okay, it may happen that for some pairs of nodes, LD, right, for some pairs of nodes, PL may be greater than PD. But if this happens, I will penalize. Look at this one. PL minus PD. This is the penalization component amount. And H is basically a constant. Right? I mean, I would say that you can think of H as a function, right? Which basically takes this value, PL minus PD, and it will return something. And you can basically use PL minus PD, forget about the function. Okay, but just trying to make it generalized. Whenever I encounter wrong thing, that would basically penalize, because this would add to the optimization function, and I'm trying to minimize it. So this will be discouraged. I would try to score the nodes in such a way that this would always be negative, right? PD is always, because if this is negative, then it would be minus, right? And then it would be better. And lambda is a hyperparameter. Okay, so this is kind of a loss function, right? Now this is the regularizer, regulation parameter. Now this is something that now we want to maximize, minimize. Okay, so let's look at some functions. So what are the things that we have we basically ignored? So first one is the loss function. So loss function meaning the H, this H, right? So H takes into account PL minus PD, right? Now in the paper, basically the author used multiple such functions of H, right? It can be just max of x plus b 0, right? Some sort of squared loss function, some sort of other types of loss functions, right? And they tried with multiple such loss functions. Now, how do we also did not discuss what is FW. FW is a function parameters by W, right? So in the paper, the authors used actually two types of function. One is exponent based function. So exponent based is basically right, exp exponent W times the feature value, the feature matrix, or it can be a logistic kind of function, which is 1 by 1 plus exponent of W times the feature. Okay, now these are something that we learned. So then what we do once we get this optimization function, we take the derivative of this with respect to W, right? In the book you see the entire derivation, and we see how to, and it's not that easy, by the way, the derivation, because of many, you will see chain rules and a lot of things. So and in this manner you basically get the values of W. Okay. Impact of now think about it. There are some parameters, hyperparameters, right? W is a parameter that you learn. Hyperparameters are lambda, right? Hyperparameters are also alpha, right? So alpha is something which basically indicates the restart probability, right? So if alpha is 0, then what would happen? If alpha is 0, then you just consider this component, meaning there is no jump as such. So in that case, if alpha is 0, then essentially this the random walk process just follows the strength matrix. This is not random walk with restart. If alpha equals to 1, then this part would be 0, meaning that it jump, it basically move and then again jump, move and jump. It would not move further, right? It would basically be restricted within one hop, right? So if alpha equals to 1, then the random walk will not move further. If alpha tends to 0, then it basically moves further. Okay, so you basically take a balance between 0 and 1. You take a you set an intermediate value, right? Similarly, if lambda, which is another hyperparameter, the regularization parameter, if lambda is 0, then it is basically same as this one, hard optimization, right? If alpha is, if lambda is 1, then you basically you overfit, you underfit. Okay, you basically give a lot of weightage to the penalization part. Okay, the derivations are there in the slide. The derivations are also there in the book, so you can look at it, and you can. The problem here is that in the supervised random walk process is that it is slow. Why? Because for every node you need to do all this random. You need to do random walk with this start. And although there are multiple tricks, in fact, we also wrote a paper to make it scalable and so. But it's turns out to be the algorithm. In general, the idea turns out to be very effective. Okay, where you basically capture the topological structure by saying that I will move my random walker through those edges or through those pairs whose strength is high. So we measure the strength based on the features. We measure we identify the positive nodes and negative nodes based on the topology, and we basically use both of them in a systematic manner. Okay. All right. So thanks. I stop here, and this is the end of this chapter. So, and in the next lecture, we'll discuss the next part. Okay. Thank you.